Good morning. Before going to Pauli's antisymmetry principle in quantum mechanics, first of all, we will study what is Pauli exclusion principle. That is, no two electrons in an atom can have the same four quantum numbers. To show the different direction of spin, a pair in the same orbital is shown as, that is, this one has up spin and this one has down spin. From this figure, we understand that two electrons in the same orbital must have opposite spins like this, not like this. To understand atomic spectroscopic data for optical frequencies, Pauli proposed exclusion principle. Exclusion principle can be applied to particles with half integral spin, which are called fermions. When two identical fermions are exchanged, the total wave function changes sign. That is, psi fermion 2 1 is equal to minus psi fermion 1 2. When two identical bosons are exchanged, the total wave function retains the same sign. That is, psi boson 2 1 is equal to psi boson 1 2. Then you should know why Pauli's exclusion principle is called exclusion principle. It is called exclusion principle because according to this principle, if one electron in an atom has same particular values for the four quantum numbers, then all the other electrons in that atom are excluded from having the same set of values. That is why Pauli's exclusion principle is called exclusion principle. The Pauli exclusion principle is one of the important principles for the arrangement of electrons in an atom along with Alpha principle and Hund's rule. Next is Slater determinant. In quantum mechanics, a Slater determinant is a simple approximate expression for a wave function of a multi-electron system. In this, each electron in a multi-electron atom must be described by a different spin orbital. It satisfies antisymmetry requirements and consequently the Pauli principle by changing sign upon exchange of two electrons. Next is how to construct Slater determinant for a helium atom in the ground stage. For a helium atom, it contains two electrons. That is, these two electrons in the 1s orbital. That can be represented as 1 by root 2 factorial, that is it contains 1 electron. Determinant 1s1, it is a 2 by 2 matrix since it contains 2 electron. 1s1 alpha 1, that is the first electron resides in the 1s orbital. Alpha 1 is the spin of the first electron. 1s1 alpha 1, 1s1 beta 1, 1s2 alpha 2, 1s2 beta 2. And on multiplication, that is cross multiplication, we get 1 by root 2 factorial, 1s1 1s2 alpha 1 beta 2 minus 1s1 1s2 alpha 2 beta 2. On taking the common terms outside, 1s1 1s2 into 1 by root 2 into alpha 1 beta 2 minus beta 2 beta 1 alpha 2. And this part, that is 1s1 1s2, represent the spatial part. That spatial part is symmetric. And this part, that is alpha 1 beta 2 beta 1 alpha 2, that represent the spin part. Spin part is antisymmetric. Spatial part cannot be antisymmetric. The spin wave function for upward spin is alpha and for downward spin is represented as beta. In the previous slide, you have studied how to construct a Slater determinant in the case of 2 electron system. This is a 3 electron system, that is lithium atom. It contains 3 electrons, that is 1s2 2s1. This is the Slater determinant in the case of 3 electron system. This is same as that you have studied in the previous slide. You have studied Slater determinant. In quantum mechanics, a Slater determinant is an expression that describes the wave function of a multi-fermionic system. It satisfies antisymmetry requirements and consequently the Pauli principle by changing sign upon exchange of 2 electrons. That is, Pauli's exclusion principle states that the total wave function of a system of pair of electrons must be antisymmetrical in the interchange of the coordinates of the pair of electrons. We can prove this. Consider a system of 2 particles described by the wave function psi 1 2, where 1 stands for all the coordinates of particle 1 and 2 for all coordinates of particle 2. It is assumed that the identical particles do not interact. Therefore, the eigenfunction for the entire system is expressed as a product of eigenfunction for individual particles. That is, psi 1 2 is equal to psi 1 into psi 2. Let psi ni denotes the normalized eigenfunction for the ith particle, where n indicates the complete set of quantum numbers needed to describe a state, then the above equation may be written as psi 12 is equal to psi n11 psi n2 2. The above wave function describes the state in which the particle 1 is in the state described by the set of quantum numbers n1, and the particle 2 is in the state described by n2. But since the particles are identical, the particle 1 may be in state n2 or 2 may be in state n1. Then we can write the symmetric as well as anti-symmetric wave function. The symmetric wave function can be written as psi s is equal to psi n11 psi n22 plus psi n12 psi n21, and the anti-symmetric wave function psi a is given by psi a is equal to psi n11 psi n22 minus psi n12 psi n21. Now, if we exchange the coordinates of electron 1 and the coordinates of electron 2, then for symmetric wave function, we get psi s dash is equal to psi n12 psi n21 plus psi n11 psi n22. Therefore, the value of psi s is equal to psi s dash. On exchanging the coordinates, we get the value same as psi s. If the coordinates of the electrons in the anti-symmetric wave function are exchanged, we get psi a dash is equal to psi n12 psi n21 minus psi n11 psi n22. Therefore, in this case, the value of psi a is equal to minus psi a dash. So far, we have considered the orbital wave functions. These are based on the quantum numbers n, l, and m. But for the complete description of the system, electron spin must be included. The electrons have a spin of plus half or minus half, and let this be expressed as alpha and beta respectively. Alpha for upspin and beta for downspin. If both electrons have spins of plus half, then the combined wave function is expressed as alpha 1, alpha 2. If both electrons have spins of minus half, then the combined wave function is expressed as beta 1, beta 2. If one electron has a spin of plus half and the other has a spin of minus half, then the combined wave function is expressed as alpha 1 beta 2 plus or minus alpha 2 beta 1. The linear combination of wave functions arises due to indistinguishability of the electrons. That is alpha 1 beta 2 plus alpha 2 beta 1 is the symmetric spin function, and alpha 1 beta 2 minus alpha 2 beta 1 is the anti-symmetric spin function. Therefore, the total wave function for the system can be expressed as a product of the orbital function and the spin function. Therefore, psi total is equal to psi n11 psi n22 plus or minus psi n12 psi n21 into spin function. This leads to 8 possible combinations. These are psi n11 psi n22 plus psi n12 psi n21 into determinant of alpha 1 alpha 2 beta 1 beta 2 alpha 1 beta 2 plus alpha 2 beta 1 alpha 1 beta 2 minus alpha 2 beta 1 and psi n11 psi n22 minus psi n12 psi n21 into determinant of alpha 1 alpha 2 beta 1 beta 2 alpha 1 beta 2 plus alpha 2 beta 1 alpha 1 beta 2 minus alpha 2 beta 1. From the above slide, we understand that there are 8 possible combinations, but only a few of these combinations are significant. This is because, according to Pauli, no two electrons in the same system can have the same values for all 4 quantum numbers. In terms of quantum mechanics, every total wave function must be anti-symmetrical in the exchange of the coordinates of every pair of electrons. According to this law, only 4 of the 8 combinations are acceptable. The acceptable combinations are, that is, psi n11 psi n22 plus psi n12 psi n21 into alpha 1 beta 2 minus alpha 2 beta 1. That is, in this case, the total wave function must be anti-symmetrical. Psi n11 psi n22 minus psi n12 psi n21 into alpha 1 alpha 2 beta 1 beta 2 alpha 1 beta 2 plus alpha 2 beta 1. In this case also, every total wave function must be anti-symmetrical. Thus, corresponding to the anti-symmetric function, there are 3 states, and corresponding to the symmetric wave function, there is only one state. The exclusion principle is a necessary feature which can be seen as follows. Therefore, psi total is equal to psi n11 psi n22 plus psi n12 psi n21 into alpha 1 beta 2 minus alpha 2 beta 1. On multiplying, we get psi n11 alpha 1 into psi n22 beta 2 minus psi n11 beta 1 into psi n22 alpha 2 plus psi n12 beta 2 psi n21 alpha 1, that is on multiplying this one, minus psi n12 alpha 2 on multiplying this one, alpha 2 into psi n21 beta 1. This can be expressed in the determinant form as psi total is equal to determinant of psi n11 alpha 1, psi n11 beta 1, psi n22 alpha 2, psi n22 beta 2 minus determinant of psi n12 alpha 2, psi n12 beta 2, psi n21 alpha 1, psi n21 beta 1. If the quantum numbers n, l and m are the same for both electrons, then psi n1 is equal to psi n2 is equal to psi n. Therefore, psi total is equal to determinant of psi n11, psi n1 alpha 1, psi n1 beta 1, psi n2 alpha 2, psi n2 beta 2 minus determinant of psi n2 alpha 2, psi n2 beta 2, psi n1 alpha 1, psi n1 beta 1. On multiplication, we get psi n1 alpha 1, psi n2 beta 2 minus psi n1 beta 1, psi n2 alpha 2 minus psi n2 alpha 2, psi n1 beta 1 minus of minus plus psi n1 alpha 1, psi n2 beta 2, that is equal to 2 psi n1 alpha 1, psi n2 beta 2 minus 2 psi n1 beta 1, psi n2 alpha 2. Therefore, psi total is equal to 2 into determinant of psi n1 alpha 1, psi n1 beta 1, psi n2 alpha 2, psi n2 beta 2. If alpha equal to beta, then psi total is equal to determinant of psi n1 beta 1, psi n1 beta 1, psi n2 beta 2, psi n2 beta 2. Thus, if all four quantum numbers are same, the total wave function is 0, which is not correct. Hence, the two electrons having the same quantum numbers cannot be in the same system.